Have you ever had a moment where reality felt off? Like something wasn't quite right, but you couldn't put your finger on it? Maybe you've had déjà vu so strong it felt like you were reliving a moment from another life. Maybe you've heard of Schrödinger's cat being both alive and dead at the same time and thought, that makes zero sense. Well, buckle up, because what you're about to learn will not only challenge everything you thought you knew about the universe, it will make you question if the universe itself should even exist. Physics is supposed to explain the world. It's supposed to tell us why apples fall from trees, why the sun burns, and why time moves forward. But hidden beneath the equations and theories, there are cracks, uncomfortable paradoxes, mind-bending contradictions, rules that seem to break reality as we know it. What if I told you that just by looking at something, you change what it is? That there are particles that can be in two places at once, until you observe them, and suddenly they choose? What if I told you that time slows down the faster you move, and that you could leave Earth today and return to find that hundreds of years have passed, while you've barely aged? And what about the universe itself? If the laws of physics were just a tiny bit different, we wouldn't exist. Did we win some cosmic lottery? Or is there something deeper, something physics hasn't yet uncovered? For the next 3 hours, we're diving headfirst into the weirdest, most confusing, and most unsettling ideas in physics. Concepts so strange that even scientists can't fully explain them. By the time we're done, you won't just see the world differently. You'll question whether the world is even real at all. So, are you ready? Because once you learn these things, there's no unlearning them. The rabbit hole is deep, and we're about to jump in. As we step into the heart of these mysteries, let's begin with something so unsettling that it reshapes our understanding of existence itself. There is an idea lurking at the core of quantum mechanics, an idea so bizarre that it forces us to question whether reality exists independently of us at all. It is called the measurement problem, and it suggests something deeply troubling. The act of observing something doesn't just reveal its state, it determines it. This isn't some fringe theory. It's not a wild guess. It is a problem physicists have been struggling with for nearly a century. The very nature of reality itself, at the smallest level, refuses to be pinned down until we step in and take a look. The universe does not simply exist in a well-defined state. Instead, before we measure it, it is an eerie cloud of possibilities, a ghostly wave of maybes, a probabilistic blur that only sharpens into a definite form when observed. This changes everything. It challenges the idea that the world exists in a concrete, objective way, separate from our perception of it. If reality is shaped by our observations, what does that mean about the world when no one is looking? Does the moon still exist when you're not staring at it? Do the objects around you have a definite form when you're not there to see them? And if observation shapes reality, then who or what first observed the universe? This is where things get complicated. The measurement problem isn't just some academic curiosity. It exposes a crack in the foundation of physics itself. It raises unsettling questions about free will, consciousness, and the very nature of existence. If reality is undefined until we measure it, then are we creating reality as we go? Or is something else at play, some hidden mechanism beyond our understanding? Physicists have tried to explain it in many ways, but each attempt leads to more paradoxes, more contradictions, more disturbing conclusions. This is not a solved problem. It is an open question, a haunting reminder that, even after centuries of progress, we may not truly understand the world at all. To understand just how deep this rabbit hole goes, we need to start with something simple: light. Light behaves in ways that should not be possible. It can travel as a wave, spreading out like ripples on a pond, but it can also hit a target as a particle, a single tiny point of energy. It does both at the same time until someone dares to measure it. The moment we look, the wave-like behavior disappears and light behaves as a particle. But here's the twist. The change doesn't just happen when we look. It seems to happen because we look. Before the measurement, light exists as an undefined probability wave, capable of taking multiple paths at once. But the second we observe it, reality chooses a single outcome. The other possibilities vanish as if they were never real to begin with. And this isn't just true for light. This behavior applies to electrons, atoms, and every fundamental building block of the universe. Everything around you, the chair you sit on, the air you breathe, the very cells in your body, is made of quantum particles that once existed in multiple states until they were observed and forced into a single reality. But what exactly counts as an observation? That's where things become unsettling. Does it require a human consciousness? Can an inanimate object measure something? Does the universe have an observer-independent reality, or is reality shaped by some form of awareness? Some physicists believe that measurement doesn't require human consciousness at all. Instead, they argue that any interaction between particles counts as a measurement. When an atom collides with another atom, it is measuring the other's position and defining its reality. In this view, observation is just another word for interaction. But others take a more radical approach. They suggest that consciousness itself plays a role in shaping reality. The moment a conscious observer looks at the system, the wave function collapses, and a definite outcome is chosen. This idea, called the consciousness causes collapse interpretation, implies that reality does not truly exist in a well-defined state until it is observed by a sentient being. If this is true, it has profound implications. It means that you play an active role in the creation of reality. It means that your perception is not just a passive window through which you view the universe, it is a force that shapes it. But if the universe does not have a definite state until it is measured, then what was happening before life existed? Before consciousness arose? Did the universe remain in a state of pure possibility until the first observer appeared? And if so, what counted as the first observer? Was it the first living organism, the first complex brain, or something else entirely? To make things even stranger, experiments have shown that this process is not limited by time. The infamous delayed choice experiment, a variation of the double slit experiment, suggests that choices made in the present can retroactively determine what happened in the past. That means the universe is not just shaped by what we observe, but also when we observe it. So where does this leave us? Physicists have proposed many solutions, but none are entirely satisfying. Some suggest that reality splits into multiple parallel worlds every time a measurement is made, so all possibilities exist, but in different universes. Others believe there is a hidden layer of physics we have yet to uncover, something that determines outcomes behind the scenes. And some argue that the question itself is flawed, that we're trying to impose classical logic onto a universe that does not obey classical rules, that our brains, evolved to survive in a world of solid objects and predictable events, are simply not equipped to comprehend the true nature of reality. But one thing is clear. The measurement problem is not just a technical issue in quantum mechanics. It is a direct challenge to everything we think we know about existence. It tells us that reality, at its most fundamental level, does not follow the neat and orderly rules we expect, that it is unpredictable, fluid, and shaped by the very act of observation. And if observation is what makes reality real, then what does that make you? Are you merely an observer, watching the universe unfold? Or are you, in some way, the creator of the reality you see? If reality is shaped by observation, then what exactly are we observing? Is the world made up of tiny particles, little building blocks that make up everything? Or is it a vast sea of waves, fluid and ever-changing, rippling across space? The answer should be simple. It should be one or the other, but it isn't. Light, one of the most fundamental elements of our universe, refuses to be placed in a single category. It acts like a wave, spreading out and interfering with itself. Yet at the same time, it behaves like a particle, a concentrated package of energy that strikes in precise points. When one looks closer, the very concept of a thing dissolves into something stranger, something beyond human intuition. The paradox is not limited to light. Matter itself, the atoms that make up everything in existence, follows the same absurd rule. The very particles that make up your body, your hands, your thoughts, do not settle into a single form. They exist in a liminal space between two opposing identities, switching between wave and particle depending on how they are observed. This defies classical logic. It contradicts everything that was once thought to be true about the physical world. If something can be both a wave and a particle, what does it actually mean to be anything at all? The very foundation of physics is shaken when the things we call objects turn out to be nothing more than flickering probabilities, uncertain until forced into form. For centuries, scientists tried to explain what light truly was. Newton believed it was made up of tiny particles, or corpuscles, which traveled in straight lines. But as experiments grew more sophisticated, another picture emerged. Light spread out. It interfered with itself, creating patterns only waves could make. It could bend around obstacles, overlap, and merge, something no particle should be able to do. The evidence was undeniable. Light was a wave. Yet, as the 20th century approached, experiments began to contradict that understanding. When light struck a metal surface, it didn't behave like a wave spreading its energy evenly. Instead, it acted like a concentrated particle, transferring energy in precise, discrete amounts. These were called photons, individual packets of energy, striking in specific locations as if light were made of tiny, indivisible units. For the first time, light was both. It spread like a wave, interfered like a wave, but hit like a particle. The paradox had no explanation. The implications went deeper than expected. If light, which was supposed to be simple and fundamental, could not decide whether it was a wave or a particle, what about everything else? Were electrons, once thought to be tiny specks of matter, actually waves too? Were atoms not the solid, well-defined objects scientists had believed them to be? Experimentation provided an answer that was even more unsettling. A simple test was devised. Fire a single electron at a barrier with two slits. If electrons were particles, they should pass through one slit or the other, like tiny bullets flying through gaps in a wall. If they were waves, they should spread out, passing through both slits at the same time, creating an interference pattern on the other side, just like ripples in water. The results were clear. Electrons, just like light, created wave-like interference patterns. They were not just single points of matter, but spread out waves of probability, capable of existing in multiple places at once. But the paradox deepened when scientists tried to measure which slit the electron passed through. The moment they placed a detector to observe it, the wave function collapsed. The electron stopped behaving like a wave and instead became a particle, passing through only one slit. The mere act of observation forced it into a definite state, as if reality itself was waiting for someone to look before making up its mind. The deeper the investigation went, the stranger the universe became. The mathematics of quantum mechanics demanded that all particles exhibit this wave-particle duality. An electron, a neutron, even an entire atom could exist as a spread-out wave, shifting through space as a probability cloud, yet behave like a solid, definite particle when measured. This raised unsettling questions. If everything was governed by quantum mechanics, what about larger objects? What about human beings? Could an entire person exist in a state of probability, only taking shape when observed? In the classical world, everything follows a logical structure. Objects are either here or there. They move in predictable ways. They do not flicker between multiple realities or shift between states based on observation. But at the quantum level, this certainty breaks apart. The mathematics governing wave-particle duality suggests that every quantum entity is not just a thing in space, but a wave of possibilities. These waves describe where a particle could be, not where it is. Until something forces the particle into a definite state, it is not confined to one reality, but exists in all possible realities at once. This uncertainty is not due to limitations in our ability to measure. It is built into the fabric of existence itself. Heisenberg's uncertainty principle states that the more precisely we try to measure a particle's position, the less we can know about its momentum, and vice versa. The universe does not allow complete knowledge of both at once. It is as if reality is fundamentally blurred, refusing to give up all of its secrets at the same time. This leads to a troubling realization. The classical world of definite positions, solid objects, and fixed identities is nothing more than an illusion. Beneath it lies a universe made of ghostly waves, shifting and uncertain, where things only become real when forced into a measurement. The conflict between the quantum world and our everyday experience remains one of the biggest unresolved problems in physics. If every particle exhibits wave-particle duality, why do we not observe it in the large-scale world? Why do people, chairs, and planets behave as definite objects rather than flickering clouds of possibility? One explanation is decoherence. The more a quantum system interacts with its environment, the more its wave-like nature collapses. Particles in isolation can exist as probability waves, but the second they interact with countless others, such as air molecules, photons, or even the vibrations of nearby atoms, their wave function collapses into a single outcome. This transition from quantum uncertainty to classical definiteness happens so quickly and so thoroughly in large systems that the strangeness of wave-particle duality disappears at macroscopic scales. Yet, this is only a partial explanation. The deeper question remains, what is reality when we are not looking? If electrons and photons behave like waves of possibility before being measured, then what is their true nature? Is everything a wave reduced to a particle only when forced into observation? Or are they particles that merely behave like waves under certain conditions? Physicists have attempted to answer this with multiple interpretations. Some believe the wave function is not a physical reality, but a mathematical tool, a way to describe probabilities without implying that a particle truly exists in multiple places at once. Others argue that the wave function is real, that everything is fundamentally a wave, and the illusion of particles arises only when we take a closer look. And then there are those who suggest a more radical solution. The many worlds interpretation states that every possible outcome of a quantum event actually happens, but in separate, parallel universes. In this view, an electron does not choose one slit to pass through. Instead, it takes both paths, but in different versions of reality. Every time a quantum event occurs, the universe splits, creating countless parallel worlds where every possible outcome plays out. This theory, if true, means that reality is far larger than anyone ever imagined. It suggests that every moment, every decision, every tiny quantum fluctuation results in a branching of existence itself, with infinite versions of reality diverging endlessly into the unknown. Wave-particle duality is not just a strange quirk of physics. It is a fundamental challenge to the very nature of existence. It tells us that reality does not behave the way we expect, that things are not always what they seem, and that the world we experience is only a limited slice of a much deeper, much stranger truth. Understanding it does not just change how one sees light or electrons, it changes how one sees everything. If the basic building blocks of the universe cannot be pinned down to a single identity, then what does it truly mean to be? This is not just a mystery of physics, it is a mystery of existence itself. If the universe refuses to be pinned down to a single identity, then the connections between things must be even stranger than previously thought. The idea that particles exist as waves of probability, shifting between possibilities until observed, was already unsettling. But the deeper question is this: what happens when two particles become linked, when their states are not just uncertain but dependent on each other, no matter how far apart they are? This is where quantum entanglement reveals itself. It is not just a peculiar feature of physics. It is a direct assault on everything once thought to be fundamental. Two particles, separated by vast distances, can be so deeply connected that a change in one instantly affects the other. The influence is immediate. No signal is sent. No delay occurs. The change happens faster than light could travel between them. This defies common sense. It violates everything relativity tells us about how information moves through space. If communication cannot exceed the speed of light, then how can one particle know what happened to another in an instant, no matter the distance between them? This connection is not limited by physical separation. Whether the entangled particles are an inch apart or spread across galaxies, they behave as if they are part of a single unified system. Einstein called this spooky action at a distance, dismissing it as an absurd consequence of quantum mechanics that must eventually be explained away. He refused to accept that nature could operate in such a bizarre fashion, but the experiments proved otherwise. Entanglement is not an illusion or a mathematical loophole. It is real, and it has been demonstrated repeatedly. The paradox is unavoidable. Two entangled particles start as a single system, bound together by the same quantum state. When they separate, their connection remains. Measuring one instantly determines the state of the other, even if they are light years apart. This is not a delay in communication. It is not a hidden force traveling between them. It is an instantaneous effect, something that should not be possible within the framework of classical physics. To understand why this breaks reality, the nature of quantum states must be examined. In classical physics, objects have well-defined properties regardless of whether they are observed. A spinning coin, even if unseen, is either heads or tails. It does not need an observer to give it a state, but quantum mechanics operates differently. Particles do not possess definite properties until they are measured. An entangled pair does not consist of two individual particles with independent states. Instead, they exist in a shared wave function, an interconnected system where neither has a separate identity. If two entangled particles are created and sent in opposite directions, their states remain linked. The measurement of one forces an outcome in the other, no matter the distance. If one is found to be spinning clockwise, the other must be counterclockwise. If one is polarized in one direction, the other must align accordingly. These results are always correlated, even though no physical connection remains between them. This suggests that information about the state of one particle is instantly known by the other. But how can this happen without breaking the speed of light limit? No classical explanation fits. There is no hidden signal passing between them. The change occurs outside the normal constraints of space and time. The implications are staggering. If entanglement allows two particles to be deeply connected beyond spatial separation, then distance itself may not be as fundamental as once thought. The fabric of reality is not simply made up of independent objects moving through space. Instead, it appears to be an underlying web of relationships where separation is an illusion and all things are part of a deeper, interconnected whole. This interconnectedness has been tested. The Bell test experiments, first proposed by physicist John Bell in the 1960s, sought to determine whether entangled particles were influenced by hidden local variables, some unknown factor carrying predetermined information between them. The results were conclusive. No hidden variable theory could explain entanglement. The correlations between entangled particles were too strong, too precise to be the result of pre-existing information. Bell's theorem confirmed what quantum mechanics had been suggesting all along. Entanglement was not a trick of incomplete knowledge. It was a fundamental property of reality itself. The universe does not operate in a local, independent manner. Instead, it behaves as if all things are connected beneath the surface. The philosophical consequences are profound. If distance does not limit entanglement, then what does this mean about the nature of space itself? If information can be correlated instantly across vast distances, then is space truly a rigid, structured entity, or is it merely an emergent phenomenon? Some physicists propose that entanglement might reveal a deeper layer of reality, one where everything exists as part of a vast, indivisible system. Instead of a universe filled with separate objects moving through space, reality may be more like a single, unified field, one where particles are not distinct entities, but manifestations of the same fundamental essence. This challenges the conventional understanding of causality. If one entangled particle instantly reflects changes in another, then could time itself be influenced by these quantum connections? Could events in one location be influenced by measurements taken in another, even before those measurements occur? There are theories that push this idea further. The concept of quantum retrocausality suggests that entanglement is not just a present connection between two distant particles. It might also allow for effects to reach backward in time. If entangled systems remain connected across space, why not across time as well? Could a choice made in the future determine a state in the past? Though speculative, these ideas hint at something far stranger than anyone expected when the laws of physics were first written. Space may not be a rigid structure. Time may not be a one-way arrow. Instead, everything may be part of a vast, entangled network where reality is shaped by relationships rather than individual objects. Beyond the theoretical, entanglement is not just an abstract curiosity. It has practical implications. The strange, non-local nature of entangled particles is being explored for use in quantum computing and cryptography. Quantum computers rely on the delicate, interconnected states of qubits, quantum bits that exist in multiple states simultaneously, to perform calculations far beyond the capabilities of classical computers. Entanglement also promises revolutionary advances in secure communication. Quantum cryptography takes advantage of entanglement's sensitivity to observation. Because measuring an entangled particle disrupts its state, any attempt to eavesdrop on a quantum encrypted message would be instantly detectable. This could lead to a new era of unbreakable encryption, where information is protected by the very laws of physics themselves. Yet despite these applications, the mystery remains. What is entanglement? Why does the universe behave this way? If particles can influence each other across vast distances, then what other hidden connections exist? Are human beings, composed of countless entangled particles, also subtly connected in ways science has yet to uncover? The more entanglement is studied, the clearer it becomes that the classical view of reality, where objects are independent, where space is an absolute barrier, where time moves in a straight line, is incomplete. The world is not made of isolated things. It is made of relationships. Entanglement is not an anomaly. It is a clue, a whisper from the deepest layers of reality, hinting at something more profound than the human mind can fully grasp. If everything is connected at a fundamental level, then what does that mean about the nature of existence itself? If information, particles, and even time are intertwined beyond the limits of space, then what else remains hidden in the quantum depths? Reality, once thought to be predictable and logical, now reveals itself as a vast, interconnected puzzle, one where the answers may be forever entangled beyond our reach. If space itself is an illusion of separation, if time can be influenced by the strange bonds of quantum entanglement, then the way the universe experiences motion must be even stranger. Moving through space is something that should be simple. Objects travel from one place to another, distances remain constant, and time moves forward at the same steady pace. But this is only an illusion. The faster something moves, the more warped time and space become. Everything that has ever been known about reality, about time ticking forward, about distances staying the same, about the very way people perceive motion, crumbles when speed approaches the ultimate cosmic limit. The speed of light. In the strange framework of relativity, time is not absolute, space is not fixed, and nothing is as stable as it once seemed. The passage of time itself is not universal. A clock moving at high speed ticks slower than one at rest. A traveler racing near the speed of light will experience time differently than those left behind. A journey lasting mere minutes for the traveler could mean years for those watching from afar. The faster one moves, the slower time flows, stretching out moments into eternity. The universe does not allow contradictions. If time can change, then space must change as well. Length itself is not absolute. The faster an object moves, the more compressed it becomes in the direction of motion. A spaceship approaching the speed of light would shrink, flattening as though squeezed by an invisible force. To an outside observer, its length would appear drastically shorter than when at rest. The object itself would not feel any change. Its own perspective remains unchanged, but the way others see it would be dramatically different. This is not an illusion or a trick of perception. It is a direct consequence of the way space and time are intertwined. In the universe, motion is not separate from time. The two are bound together in a single entity, space-time. The speed at which one moves through space determines the speed at which one moves through time. Those who remain still experience time at its normal rate. Those who move quickly take a different path, one where time flows more slowly. This is not just an abstract theory, it is a measurable fact, proven by the very nature of the cosmos itself. Satellites orbiting Earth experience time at a different rate than clocks on the surface. GPS systems must account for the effects of time dilation, or their readings would drift and become wildly inaccurate. The difference is small at everyday speeds, but it grows as motion approaches the speed of light. At the extreme, time itself would nearly come to a halt. A traveler moving at 99.999%, the speed of light would barely age, while centuries pass for those standing still. This is not merely a mathematical curiosity. It is the key to understanding the deepest structure of reality. Time is not a rigid, universal flow. It bends, stretches, and warps based on motion. The implications are staggering. If one were to leave Earth on a journey at near light speed, a short trip by their own experience could mean that when they return, generations have passed, civilizations have changed, and the world they knew is gone. The very concept of simultaneity collapses in this framework. There is no single now that applies to all observers. What is the present for one person may be the past for another, depending on their motion. The faster someone moves, the more their experience of time diverges from those left behind. In extreme cases, Two observers may disagree not just on how much time has passed, but on which events happened first. Einstein's theory of relativity shattered the classical idea that time and space were fixed. Before relativity, physics assumed that distances remained the same no matter how fast something moved. Time was believed to flow at a constant rate, the same for all observers. But the reality is different. The speed of light is the only true constant. Everything else, time, space, motion, must shift to ensure that this cosmic speed limit is always obeyed. This means that no matter how fast one moves, light will always travel at the same speed. A person chasing after a beam of light at nearly the same speed will still measure it moving away at the same speed as someone standing still. The universe bends time and space to preserve this rule. The passage of time slows, lengths contract, and reality reshapes itself to maintain the absolute nature of light. The consequences go deeper. If time slows down as speed increases, then at the speed of light itself, time would stop entirely. A photon, a particle of light, experiences no passage of time at all. From its perspective, the moment it is created is the same moment it reaches its destination. For light, the entire universe is compressed into a single instant. This idea rewrites what is understood about movement. Speed is not just about traveling through space, it is also about traveling through time. At normal speeds, motion through time dominates. People experience the passage of seconds, minutes, and years without noticing any change. But as speed increases, movement through time slows, shifting the balance towards movement through space. At the speed of light, all movement through time ceases. This is why no massive object can ever reach the speed of light. The closer something gets to this cosmic limit, the more time slows. To reach light speed, time would have to stop entirely. The energy required to accelerate an object to this point becomes infinite. Nothing with mass can achieve this state. Only massless particles, like photons, are able to move at the speed of light, existing outside the normal flow of time. Yet, despite these constraints, the strange effects of relativity have been tested and confirmed. Muons, subatomic particles created by cosmic rays in the atmosphere, should decay too quickly to reach the surface of the Earth. But because they travel at nearly the speed of light, time slows down for them, extending their lifespan just long enough to survive the journey. Their movement bends time itself, allowing them to exist longer than they would otherwise. These distortions of time and space are not just theoretical predictions. They are built into the very fabric of the universe. Every motion alters the passage of time. Every speed affects the length of objects. Every observer experiences reality differently based on their state of motion. The idea that time slows and objects shrink as speed increases defies common experience. In daily life, motion seems ordinary, distances remain constant, and time marches forward at a predictable rate. But this perception is a limitation of human senses, not a reflection of reality. In a universe where space and time are fluid, shaped by motion, the fundamental nature of existence is far stranger than intuition suggests. What is considered real is not fixed, but dependent on perspective. One traveler may experience moments that stretch into decades for another. An object at high speed is not what it seems, its shape altered by the very act of movement. The connection between time and speed suggests deeper questions. If time is not absolute, then what does it mean to age? If two people can experience different amounts of time based on their motion, then what defines reality? The flow of time is not a single thread. It is a shifting, changing fabric, woven differently for every observer. In a world where speed controls time, where distances change based on motion, and where the experience of reality itself is shaped by movement, the universe is not what it once seemed. Motion is not just a journey through space, it is a journey through time, one where the rules bend, stretch, and break the boundaries of classical thought. If time itself is not fixed, if distances are fluid, if nothing is truly constant except the speed of light, then what does this say about the true nature of existence? If every moment is relative, then what is real? If the future for one is the past for another, then is time even a meaningful concept at all? The more deeply the effects of relativity are explored, the more they reveal that reality is not bound by common experience. What seems obvious, time ticking forward, distances remaining the same, objects holding their shape, is an illusion created by the narrow limits of human perception. Beneath this illusion lies a universe that does not obey simple rules. Nothing is fixed. Everything is relative, and the deeper the motion, the stranger the truth. If time is not absolute, if it bends under motion and slows near the speed of light, then why does it still appear to move in only one direction? The fundamental laws of physics do not place any preference on forward or backward movement in time. The equations work equally well in both directions, yet in reality, everything moves forward. Moments pass, the past remains unreachable, and no event can be undone. But if nothing in the fundamental laws prevents time from reversing, then why does time flow only one way? Every experience confirms that time has a direction. A cup shatters but never reassembles. People age but never grow younger. Memories form of the past but never of the future. The universe itself expands outward, galaxies drifting apart, never compressing back to an earlier state. The world is filled with irreversible events, yet the equations that govern the movement of particles and forces remain symmetrical in time. If physics treats past and future the same, then what is enforcing this one-way flow? The problem is deeper than it seems. Everything from human experience to the vast evolution of the cosmos is dependent on time having a direction. If time had no preference, there would be no past, no future, only a shifting state of existence that does not favor movement in one direction over the other. Yet no one has ever observed time reversing, even at the microscopic level, even in the domain of quantum mechanics, where uncertainty rules. Events unfold forward. One of the most compelling explanations comes from the nature of entropy, the measure of disorder in a system. The second law of thermodynamics states that entropy always increases over time in an isolated system. This law is the foundation of irreversibility. It explains why heat flows from hot to cold, never the other way around. It explains why mixing different substances is easy, but separating them again requires effort. Entropy gives time its arrow. In the early universe, everything was in a highly ordered state. As time progressed, disorder increased, and systems evolved toward greater complexity. The universe itself began in a low entropy state, and since then, it has been marching toward greater disorder. The expansion of the cosmos spreads matter outward. The formation of stars and galaxies follows this thermodynamic principle, and even the decay of energy ensures that systems move forward rather than backward. This raises an unsettling question. If entropy is what gives time its direction, then why was the universe in a low entropy state to begin with? If everything trends toward disorder, then why did it start in an ordered condition? The answer to this remains one of the greatest mysteries in physics. Some theories suggest that the early universe, born from the Big Bang, was in a state of extreme simplicity, not because of some fundamental rule, but because of the way space itself was structured at that time. As space expanded, complexity naturally emerged and entropy increased. Others propose that the arrow of time is not an intrinsic property of reality, but an emergent feature, something that arises only because humans exist within a universe where entropy appears to be increasing. But the problem is not limited to thermodynamics. The question extends into the nature of causality itself. If time were reversible, then events could loop, causes could follow their effects, and sequences of actions could undo themselves. Reality does not work this way. Events unfold forward because they depend on previous conditions. The relationship between time and causality is a delicate one. If the universe allowed time to flow in both directions, cause and effect would lose meaning. The future would not be distinct from the past. A signal could be sent backward in time, creating paradoxes where an effect occurs before its cause. The consistency of the universe depends on the preservation of time's direction. Yet, in physics, time reversal symmetry is not entirely dismissed. At the smallest scales, certain interactions appear nearly symmetrical. In some cases, individual particle reactions look the same when played in reverse. But even at this fundamental level, a subtle asymmetry exists. The weak nuclear force, responsible for radioactive decay, breaks time reversal symmetry. Certain particle interactions favor forward motion in time over backward motion. While tiny in effect, this slight imbalance reinforces the larger cosmic preference for time moving forward. Even more troubling is the idea that time's direction might not be an absolute feature of the universe, but instead something dependent on perspective. If an observer existed outside the known universe, would they experience time at all? Could there be regions of the cosmos where time behaves differently, flowing at different rates, or even reversing under certain conditions? The concept of a cyclic universe suggests that time itself might have a broader structure than currently understood. Some theories propose that after eons of expansion, the universe could eventually collapse in on itself, resetting the conditions of space, energy, and time. If this were the case, then time as experienced in one cycle might not be the same as time in another. While no evidence currently supports this idea, it raises the possibility that the arrow of time might not be eternal, but rather a temporary feature of the universe's current state. Black holes complicate the question further. Inside a black hole, time behaves differently from anything known in ordinary space. As an object falls toward the event horizon, time slows relative to an outside observer. At the singularity, the equations break down entirely, suggesting that within such extreme conditions, the very fabric of time itself might be fundamentally altered. If black holes warp time, then could similar effects exist elsewhere in the universe? Could there be places where time's forward flow is weakened, distorted, or even reversed? While nothing has been observed to suggest such regions exist, the laws of physics do not fully rule out the possibility. Another perspective comes from the role of quantum mechanics in time's asymmetry. Quantum wave functions evolve in both directions, but when a measurement is made, the wave function collapses into a single outcome, reinforcing the forward direction of events. If measurement is what forces quantum systems into definite states, could it also play a role in defining time's irreversible nature? Some physicists argue that time's one-way flow may be an emergent property rather than a fundamental rule. If the universe is a vast collection of interacting systems with countless microscopic processes occurring at every moment, then the collective effect of these interactions might generate the perception of forward-moving time. There is also the unsettling possibility that time itself may not be fundamental at all. Some theories suggest that time is an illusion, a byproduct of deeper physical laws that do not contain time as a basic element. If true, then the reason time moves forward may not be a question of physics, but one of human perception. Consciousness itself may play a role in defining time's arrow, shaping reality through the process of observation. This view aligns with some interpretations of quantum mechanics, where measurement is what determines the outcome of uncertain states. If perception influences reality at the quantum level, could the experience of time itself be something created by the act of observation? While no consensus exists, every exploration into the nature of time leads to more contradictions, more unresolved mysteries. The laws of physics remain indifferent to direction, yet time progresses forward. Entropy increases, yet the origins of its low starting point remain unknown. Causality enforces order, yet no absolute rule demands that it must. The deeper the investigation goes, the clearer it becomes that time, once thought to be the simplest aspect of existence, is perhaps the most complex. It is not a passive backdrop against which events unfold. It is an active, shifting, and deeply mysterious aspect of reality. If the universe began with time flowing forward, does it mean it will always do so? If time's arrow is determined by entropy, then could there be a moment, trillions of years from now, when entropy reaches a maximum and time itself ceases to have a direction? Could the universe experience an era where forward and backward no longer have meaning, where existence is frozen in an unchanging state? The search for an answer continues, but one fact remains undeniable. Every moment that passes, every irreversible action, every change that cannot be undone reinforces the reality of time's forward flow. No one has ever moved backward through time, no memory has ever come from the future, and no event has ever repeated itself in reverse. Yet, despite all efforts to explain it, time remains one of the greatest mysteries of existence. A force that should not have a direction, yet does. A concept that should be reversible, yet is not. A reality that is both known and unknowable, unfolding forward with or without understanding. If time flows irreversibly forward, if events unfold in one direction with no way to reverse their sequence, then what happens when the fundamental laws of physics suggest that reality itself does not settle into a single outcome until it is observed? Quantum mechanics presents a contradiction to the way the universe is expected to behave. It does not follow the clear-cut structure of cause and effect that dominates classical physics. Instead, it allows for something much stranger, a world where an object is not in one state or another, but in both, suspended in a paradox until a measurement forces it into reality. This unsettling truth is most famously represented by Schrödinger's cat, a thought experiment that exposes the contradictions in the quantum world. In this scenario, a cat is placed inside a box with a mechanism that can release poison based on the state of a quantum particle. If the particle decays, the poison is released and the cat dies. If the particle does not decay, the cat remains alive. The problem arises because quantum mechanics dictates that before observation, the particle exists in a superposition of both decayed and non-decayed states. Since the fate of the cat is tied to this particle, the cat, too, is in a superposition. It is both alive and dead at the same time. This is not an issue of uncertainty. It is not a matter of simply not knowing whether the cat is alive or dead. The paradox states that, according to quantum mechanics, the cat genuinely exists in both states until someone looks inside the box. The act of observation does not simply reveal an existing truth, it determines the truth. The implications of this are disturbing. If reality is undefined until it is observed, then what does it mean to say that anything exists before it is measured? Does an unobserved event truly happen? Does the moon still exist when no one is looking at it? These questions challenge the foundation of what it means for something to be real. Quantum superposition is at the heart of this paradox. In classical physics, an object has a definite state regardless of whether someone is observing it. A coin is either heads or tails, even before it is flipped. A door is either open or closed, regardless of whether anyone is there to see it. But in the quantum world, things do not behave this way. a particle does not have a single definite state until it is measured. It exists in multiple possibilities, all of them real, until forced into a single outcome. The Schrödinger's cat thought experiment was designed to highlight the absurdity of applying quantum mechanics to large-scale objects. Particles are known to behave in superpositions, but no one has ever observed a cat, a person, or any macroscopic object existing in two opposing states simultaneously. Yet, the mathematics of quantum mechanics does not draw a clear boundary between the microscopic and macroscopic world. If quantum rules apply to atoms and atoms make up everything, then why do people experience a world where things exist in single, definite states? One interpretation suggests that measurement forces reality to choose. The moment an observer interacts with a quantum system, the wave function collapses, and only one outcome becomes real. Before measurement, all possibilities coexist in a delicate balance, but the act of observing forces nature to select a single state. This view aligns with what is seen in experiments like the double slit experiment, where particles behave as waves until measured, at which point they suddenly behave like discrete particles. Yet, this explanation raises a deeper problem. What counts as measurement? Does it require a conscious observer? Could an inanimate detector collapse the wave function? Or does reality only solidify when a mind perceives it? The question of what qualifies as an observer is one of the most unsettling mysteries in quantum mechanics. If consciousness is required, then does that mean reality itself depends on the existence of observers? Some physicists reject the idea that measurement collapses the wave function. The many worlds interpretation proposes a radical alternative, that every possible outcome of a quantum event actually happens, but in different branches of reality. In this view, Schrödinger's cat is never in a superposition at all. Instead, the universe splits the moment the quantum event occurs, one branch where the cat is alive, another where the cat is dead. Each possibility is realized, but in separate versions of reality. This idea removes the need for a wave function collapse. Instead of choosing a single outcome, the universe allows all possibilities to unfold, each in its own parallel existence. But if this interpretation is correct, then reality is constantly branching into countless versions, creating an infinite number of parallel worlds at every moment. Every quantum event, every decision, every microscopic fluctuation results in a universe splitting off, where both possibilities become real in different timelines. Yet, despite its appeal, the many worlds interpretation does not explain why humans experience only one reality. If every possibility happens, then why is there no awareness of the other branches? Why does a person remember a single history rather than an infinite collection of alternative paths? Another interpretation suggests that quantum mechanics does not describe an incomplete reality, but rather an underlying statistical structure. The Copenhagen interpretation, one of the most widely accepted explanations, argues that the wave function represents a set of probabilities rather than physical reality. In this view, quantum mechanics does not describe objects existing in two states, but rather the likelihood of different outcomes. When a measurement is made, one of those possibilities becomes certain, but the wave function was never a description of actual coexistence. It was a mathematical tool for predicting probabilities. Yet, even this does not fully resolve the paradox. The wave function may be a probability distribution, but until it collapses, it still allows for strange effects like quantum entanglement and superposition. A cat being both alive and dead may be a thought experiment, but at the particle level, something equally strange happens every moment. Experiments confirm that superposition is real. Particles routinely exist in multiple states until measured. Quantum computers rely on this principle, using qubits that can hold multiple states at once, exponentially increasing computational power, but the transition from microscopic quantum effects to macroscopic reality remains unexplained. Some researchers propose that decoherence resolves the issue. When a quantum system interacts with its environment, its wave function collapses naturally due to the overwhelming influence of external factors. In this view, Schrödinger's cat never actually exists in a visible superposition because the interactions with air molecules, photons, and thermal vibrations cause an immediate collapse into a definite state. Yet, even if decoherence explains why large objects do not appear to exist in superpositions, it does not eliminate the core mystery. Why quantum mechanics, which governs everything, allows for such contradictions in the first place. The implications stretch beyond physics into philosophy and metaphysics. If reality only becomes definite when observed, then what does it mean for something to exist in an unobserved state? If all possible outcomes play out in separate realities, then is the experience of a single timeline merely an illusion of limited perception? The deeper the thought experiment is examined, the more it suggests that reality is not what it seems. The everyday experience of a world with clear outcomes, distinct moments, and definite states is only one layer of existence. Beneath it lies a structure where things exist as probabilities, where events unfold in parallel, where observation itself defines what is real. Schrödinger's cat is more than a paradox. It is a doorway to the unresolved contradictions at the heart of physics. It forces the mind to confront a reality that is not fixed, not singular, but fluid and undefined until observed. If a cat can be both alive and dead, if reality can exist in multiple states until it is forced into one, then what does this mean about the nature of existence? If measurement defines reality, then who or what is measuring the universe itself? The question remains unanswered, but what is certain is that the act of looking, the simple act of observing, does not just reveal reality, it shapes it, and that realization changes everything. If reality only takes form when observed, if objects exist in a blur of probabilities until measured, then what happens when the act of observation itself determines the outcome of an event? The paradox of Schrödinger's cat suggests that existence is not set in stone until a measurement is made. But how far does this principle extend? Is it limited to isolated quantum systems, or does it reveal something much deeper about the way the universe fundamentally operates? The answer lies in one of the most famous experiments in the history of physics, the double-slit experiment. A simple setup that should have confirmed the ordinary nature of light and matter instead exposed a disturbing truth. Particles do not behave in a predictable, classical way. They shift, change, and adjust their nature based on whether or not they are being observed. This single experiment forces a confrontation with the most unsettling question in physics. Does reality exist independently of observation, or is it shaped by the mere act of looking? The experiment involves sending particles, electrons, photons, or even entire atoms through a barrier with two slits. If these particles were like tiny bullets, they should pass through one slit or the other and form two distinct patterns on a detection screen. But when no measurement is made, something impossible happens. The particles behave like waves, spreading out and interfering with themselves, forming an interference pattern. This means that each particle is somehow traveling through both slits at once, behaving as a wave of probabilities rather than a definite object. Yet, when a measuring device is placed at the slits to determine which path the particle takes, everything changes. The interference pattern disappears, and the particles suddenly behave like tiny solid objects again, passing through only one slit. The very act of measurement forces them into a definite state, erasing their wave-like behavior. This contradiction is not limited to light. It happens with electrons, atoms, and even molecules large enough to be seen under an electron microscope. Every time a measurement is made to determine which path the particle takes, the outcome is altered. The presence of an observer disrupts the natural state of the system, forcing it into one outcome rather than allowing for multiple possibilities. This is not just a technical curiosity, it is a direct challenge to the classical view of the universe. In the everyday world, objects move along clear paths. A thrown rock does not take multiple trajectories at once. A car does not split into probabilities and merge back together. But at the fundamental level of reality, this certainty vanishes. Particles act as waves of potential, shifting between multiple realities until forced to choose a single state. The implications go beyond physics. If observation collapses a quantum wave function, then what qualifies as an observer? A measuring device does not possess consciousness, yet it still disrupts the interference pattern. Does the mere interaction with any external system count as an observation? Or is there something unique about a conscious mind that finalizes reality? Some interpretations suggest that the wave function is not a physical entity, but a tool for predicting probabilities. In this view, the particle does not truly exist in multiple places at once. It only has a set of potential outcomes until one is observed. The collapse of the wave function is simply a shift from a range of probabilities to a single definite state. But this explanation does not eliminate the central mystery. If a particle was always going to take a specific path, then why does the interference pattern disappear when measured? Another explanation is that reality does not collapse into a single outcome at all. Instead, the universe splits. Every time a quantum measurement is made, the world branches into multiple versions, each representing a different possibility. In one reality, the particle passes through the left slit. In another, it passes through the right. In yet another, it behaves as a wave and forms an interference pattern. If this many worlds interpretation is correct, then every quantum event creates countless parallel universes. The observer does not force a single outcome into existence. Instead, they merely find themselves in one version of reality among an infinite number of equally real possibilities. The double-slit experiment does not show that observation alters particles. It shows that the universe is continuously splitting into different versions of itself. Yet, this idea raises another question. If multiple versions of reality exist, why do humans experience only one? Why does a person remember a single past rather than an infinite array of possible histories? If every quantum event creates a branching reality, then what determines which version of reality a conscious mind follows? The problem extends to the nature of time itself. If quantum states can exist in superposition, could they also remain entangled across time? Could an event in the future determine an outcome in the past? Certain variations of the experiment suggest that choices made in the present can retroactively influence past events. The delayed choice experiment, a modified version of the double-slit setup, shows that measuring a particle even after it has passed through the slits still affects the way it behaved earlier. This suggests that quantum reality does not merely unfold in a passive manner. The act of measurement is not simply revealing a pre-existing state. It is shaping the history of that state, altering what happened before the measurement was made. The unsettling nature of this result forces a re-examination of the entire framework of cause and effect. If an event in the present can determine the past, then does that mean time itself is fluid at the quantum level? Could the future play a role in defining the past just as much as the past defines the future? Physicists have attempted to make sense of these contradictions. Some argue that information is never truly lost, even when a quantum wave function collapses. Instead, reality follows strict conservation laws that maintain consistency across time and space. Others believe that quantum mechanics is simply incomplete, that a deeper theory exists, one that will ultimately explain why observation changes outcomes. Yet, after decades of experimentation, no such theory has emerged. The double-slit experiment remains a clear demonstration that particles behave differently depending on whether they are being watched. This suggests that either observation influences reality or reality consists of an infinite web of parallel possibilities. The implications extend into technological advancements. Quantum computing relies on the ability of quantum systems to exist in multiple states simultaneously, performing vast calculations that classical computers cannot achieve. The principles exposed by the double-slit experiment are being harnessed to develop technologies that take advantage of quantum superposition, entanglement, and probabilistic computation. Despite its practical applications, the fundamental mystery remains. If reality changes based on whether it is observed, then does that mean reality itself is an illusion? Is the physical world truly independent of observation, or is it something that only comes into existence when perceived? The challenge is not just one of physics, but of understanding existence itself. If the universe behaves differently when unobserved, then what does it mean to say that anything exists without an observer? If particles move through multiple paths until forced into a single one, then what defines reality in the absence of measurement? The double-slit experiment does not provide answers. Instead, it reveals the fragile nature of what is assumed to be real. It is a reminder that the world is not as solid as it appears, that the rules governing everyday life break down at the most fundamental levels. If an event does not take a definite form until it is observed, then what does it mean to say that reality is independent of perception? If measuring a particle changes its behavior, then what role does the observer play in shaping the universe? The experiment exposes a truth that is difficult to accept. The reality experienced is not an objective, fixed structure. It is a process, a series of interactions where observation and existence are deeply intertwined. Whether this means reality is a construct of perception, a branching web of parallel worlds, or something yet to be understood remains unknown. But one thing is certain. What was once thought to be a simple experiment has become a window into the most profound mystery of existence itself. If observation changes reality, then what ultimately is real? If observation itself determines reality, if the mere act of measuring a system forces it into a definite state, then what about the vast stretches of space where no one is watching? What fills the emptiness between galaxies, between particles, between the very fabric of existence? For centuries, space was assumed to be a void, an absence of matter, a stage upon which the universe played out its story. But deeper investigation reveals something far more unsettling. Empty space is not empty at all. It is seething with energy, a hidden force woven into the very fabric of the cosmos, a mystery that defies every prediction and threatens to overturn the understanding of reality itself. Quantum mechanics suggests that even in a perfect vacuum where no particles exist, fluctuations continue to take place at the smallest scales. The void is not silent. It is alive with activity, a restless dance of energy, appearing and disappearing, emerging and vanishing in ways that cannot be directly seen, but whose effects shape the universe. This energy, known as vacuum energy, is an unavoidable consequence of quantum field theory. The uncertainty principle dictates that particles can never truly be at rest, that fields cannot settle into absolute nothingness. There is always a residual energy, an invisible force humming beneath the surface of reality. This is not just a theoretical curiosity. The existence of vacuum energy has been confirmed through experiments like the Casimir effect, which demonstrates that empty space exerts a measurable force. Two parallel plates placed close together in a vacuum experience an attraction, not due to any external force, but because of quantum fluctuations in the vacuum itself. The energy of empty space is real, and its effects can be observed. But this leads to a far greater problem, a discrepancy so vast that it is considered one of the greatest crises in theoretical physics. When quantum mechanics calculates the amount of vacuum energy that should exist, the result is staggeringly large, 120 orders of magnitude greater than what is observed. This is not a small error. It is the largest discrepancy between theory and observation in the history of science. If vacuum energy were as large as predicted, the universe would have torn itself apart in an instant, overwhelmed by a force that should be driving space apart at an unimaginable rate. Yet, instead of catastrophe, the universe appears to be expanding at a much slower, measured pace, guided by a mysterious force known as the cosmological constant. Originally introduced by Einstein as a mathematical correction to his equations of general relativity, the cosmological constant was meant to counteract gravity and maintain a static universe. But when it was discovered that the universe was not static but expanding, the term was abandoned, thought to be unnecessary. Decades later, the unexpected happened. Observations of distant supernovae revealed that the expansion of the universe was not slowing down, as gravity should dictate, but accelerating. The cosmological constant, once dismissed, was resurrected, not as a balancing term, but as the driving force behind the accelerating expansion of the universe. The connection between vacuum energy and the cosmological constant presents an unsolved puzzle. If empty space has energy, then this energy should exert a repulsive force, pushing space apart, but the observed rate of expansion is nowhere near what quantum mechanics predicts. The discrepancy suggests that something fundamental is missing from the understanding of how vacuum energy interacts with spacetime. One possibility is that there exists a mechanism that cancels out most of the vacuum energy, reducing it to the small value observed, but no known physical process accounts for such fine-tuning. Another proposal is that vacuum energy may not be constant, that it changes over time, evolving as the universe expands. This idea aligns with certain models of dark energy, the unknown force driving cosmic acceleration, but remains highly speculative. The presence of vacuum energy also raises profound questions about the nature of space itself. If empty space contains energy, then is space truly a background upon which matter moves, or is it an active participant in the evolution of the universe? If energy permeates even the most desolate voids, then does it have structure, fluctuations, or an underlying pattern that has yet to be understood? Some theories suggest that vacuum energy might be linked to the fundamental structure of space-time. In certain models of quantum gravity, space is not continuous, but composed of discrete units, woven together like a cosmic fabric. At the smallest scales, this fabric may ripple with vacuum fluctuations, shaping the properties of reality itself. Another possibility is that the vacuum energy problem hints at the existence of additional dimensions beyond the familiar three of space and one of time. If extra dimensions exist, they may influence the amount of vacuum energy observed, altering its effects in ways that have not yet been detected. The problem grows deeper when considering the role of vacuum energy in the fate of the universe. If the cosmological constant remains unchanged, the acceleration of cosmic expansion will continue indefinitely. Galaxies will drift apart, stars will burn out, and the universe will cool into a dark, empty void. But if vacuum energy fluctuates, if it is not a fixed constant, but something that can change, then the future is uncertain. In some models, vacuum energy could decay into a lower energy state, triggering a catastrophic transformation of the universe. This process, sometimes referred to as vacuum decay, would reshape the very structure of reality, altering the fundamental constants of nature and potentially erasing everything known in an instant. The connection between vacuum energy, quantum mechanics, and gravity remains one of the greatest unresolved mysteries in physics. General relativity describes gravity on large scales, while quantum mechanics governs the smallest interactions of particles and fields. But when these two theories attempt to explain vacuum energy together, they clash. General relativity predicts one behavior, quantum mechanics predicts another, and no theory successfully unites them. This gap suggests that a deeper theory is needed, one that does not merely explain the observed value of vacuum energy, but reveals why space itself behaves as it does. Whether this theory involves hidden symmetries, undiscovered particles, or entirely new principles of physics is unknown. One of the most intriguing ideas comes from the holographic principle, which suggests that the information contained within a volume of space may actually be encoded on a lower dimensional boundary. If true, then what appears as vacuum energy within space may be the result of deeper, unseen processes occurring at the edge of reality itself. Despite the unresolved questions, vacuum energy is not just a theoretical concern. Its effects are measurable, its influence on cosmic expansion undeniable. The challenge is not proving that it exists, but understanding why it behaves the way it does. The search for answers continues in multiple directions. Some physicists investigate the mathematical foundations of quantum field theory, searching for hidden cancellations that might explain the tiny observed value of vacuum energy. Others explore modifications to general relativity, testing whether gravity itself behaves differently on cosmic scales. Observations of the universe's large-scale structure provide further clues. Mapping the distribution of galaxies, analyzing the cosmic microwave background radiation, and studying the behavior of distant quasars all contribute to refining the understanding of how vacuum energy shapes the cosmos. Yet, even with all these efforts, the fundamental question remains unresolved. If empty space contains energy, then what is the true nature of this energy? If the vacuum is not truly empty, then what unseen forces are at play within it? The implications extend beyond cosmology. If vacuum energy can be harnessed or manipulated, it could lead to technologies far beyond current understanding. Some speculative theories propose that access to vacuum energy might one day allow for new forms of propulsion, energy generation, or even control over space-time itself. But for now, the mystery remains. Space, once thought to be a void, is instead a seething ocean of hidden energy. The laws of physics predict a force so powerful it should have destroyed the universe in an instant, yet instead, it gently shapes the expansion of the cosmos. The cosmological constant, once dismissed as an unnecessary term, has returned as one of the greatest enigmas in science. The deeper the investigation, the clearer it becomes that reality is not what it once seemed. If space is filled with energy, then what else lies hidden within the fabric of existence? If the structure of the cosmos is shaped by forces that remain unknown, then what truths about reality have yet to be uncovered? The answers remain elusive, but one thing is certain: space is not empty. It is a realm of hidden forces, an arena of untapped power, a mystery that, once solved, may reshape the understanding of existence itself. If empty space is not truly empty, if the very fabric of reality contains energy that influences the evolution of the cosmos, then what does this mean for the nature of time itself? Space and time are inseparable, woven together in a structure that bends and stretches, warps and expands. But if space can behave in ways that defy intuition, can time do the same? Is time an unchangeable sequence of events, or is it something far more fluid, something that can be rewritten? The universe appears to unfold in a strict order, with cause leading to effect. Actions create consequences, and the past determines the present, which in turn shapes the future. But what happens if the future has the power to change the past? If time travel is possible, then the very logic of cause and effect collapses, giving rise to paradoxes that threaten the consistency of reality itself. One of the most famous time travel paradoxes is the grandfather paradox. It presents a scenario where a person travels back in time and prevents their own grandfather from meeting their grandmother. If successful, the time traveler is never born. But if they were never born, then how did they go back in time to change the past? This contradiction reveals a fundamental problem with time loops. Events begin to erase themselves, creating logical impossibilities. The paradox forces a confrontation with the nature of time. If the past can be altered, then does that mean the timeline branches into multiple realities? Does changing the past create a new future? Or does it overwrite the original timeline entirely? The grandfather paradox suggests that time must have built-in consistency, preventing contradictions from arising. But how could such a mechanism exist? One possible solution is the Novikov self-consistency principle, which states that time travel cannot create paradoxes because the timeline is already consistent. According to this view, any action taken by a time traveler was always meant to happen. If someone attempts to change the past, they will only end up fulfilling the events that led them to travel back in time in the first place. The universe corrects itself, preventing any alteration that would lead to logical contradictions. This approach eliminates paradoxes, but raises another issue. Does this mean that free will is an illusion? If the past cannot be changed, then time travelers are trapped in a predetermined loop, unable to make choices that would disrupt history. Every action they take must already be accounted for in the timeline. This removes the danger of paradoxes, but at the cost of denying the possibility of true change. Another perspective comes from the many worlds interpretation of quantum mechanics. If every quantum event creates a branching reality, then altering the past does not overwrite history, but instead generates a new parallel universe. In this scenario, traveling to the past creates a divergent timeline where events unfold differently, but the original timeline remains unchanged. The paradox is avoided because the time traveler does not change their own history, they create a new one. This idea aligns with the concept of the multiverse, where infinite versions of reality coexist, each representing a different sequence of events. If time travel leads to the creation of new branches, then there is no single past to preserve, only an endless web of possibilities. But this raises another question. If new timelines emerge with every alteration, then why does consciousness seem to follow only one path? If infinite versions of a person exist across multiple timelines, why does experience remain confined to a single reality? The problem deepens when considering causality. If an event in the future influences the past, then how does information travel backward through time? The standard laws of physics do not allow signals to move in reverse. However, certain interpretations of quantum mechanics suggest that information may not be limited to forward motion. Delayed choice experiments show that decisions made in the present can retroactively determine outcomes in the past. In some setups, the measurement of a particle's state appears to affect how it behaved before the measurement took place. This suggests that quantum systems may not be bound by the same rigid structure of time that governs macroscopic reality. If this principle extends to larger scales, then could information be sent backward in time without violating causality? Some physicists propose closed time-like curves, theoretical paths through space-time that loop back on themselves. These curves, permitted in certain solutions to Einstein's equations, suggest that under extreme conditions, such as inside a rotating black hole, time could bend back on itself, creating a self-contained loop where events cause themselves. But even if time loops exist, they do not necessarily allow free modification of the past. If a person steps into such a loop, do they retain their memories of the previous cycle, or are they bound to repeat the same actions over and over? If time is cyclical, does this mean history is doomed to repeat itself infinitely, with no possibility of deviation? A further complication arises when considering energy conservation. If time travel allows objects or people to appear in the past without an equivalent disappearance in the future, then mass and energy are not being conserved within a single timeline. This violation of fundamental physical laws suggests that either time travel requires a balancing mechanism, such as the creation of negative energy, or that it is only possible under specific conditions that maintain conservation laws. Attempts to create practical models for time travel often involve exotic solutions, such as wormholes. A wormhole is a theoretical shortcut through space-time, connecting two distant points through a hidden bridge. If one end of a wormhole were moved at high speeds or placed near a strong gravitational field, time dilation could create a situation where stepping through it would lead to the past. However, wormholes, if they exist, may be unstable. Quantum fluctuations could collapse them before they become usable, preventing their exploitation for time travel. Even if stable wormholes were possible, they might not allow unrestricted movement through time, only between connected points within a fixed range. Another concept is tachyons, hypothetical particles that always travel faster than light. If such particles exist, they could theoretically transmit information into the past, but no evidence for tachyons has been found, and their existence would imply deeper contradictions within relativity. The paradoxes of time travel also challenge philosophical notions of identity and continuity. If a person travels to the past and interacts with their younger self, do they remain the same individual, or has the timeline split, creating a duplicate? If an event is erased from history, does that mean it never truly happened, or does it persist in some form outside of conventional time? These questions extend beyond physics into the realm of metaphysics. If time is not fixed, if it can be altered or branched, then what defines reality? If past events can be rewritten, does that mean history is not a record of what happened, but a shifting landscape of possibilities? One perspective suggests that the universe maintains consistency through unknown mechanisms. If paradoxes threaten logical coherence, then perhaps physical laws enforce constraints that prevent reality from unraveling. Some researchers propose that hidden variables or deeper structures within space-time might govern the flow of time, ensuring that contradictions never arise. But if such constraints exist, then what determines which events are possible and which are forbidden? If the universe prevents paradoxes, then how does it decide what changes are allowed? Does an unseen force correct inconsistencies, or is the flow of time fundamentally unalterable? Despite decades of exploration, time travel remains one of the greatest unresolved puzzles in physics. The possibility of altering history leads to contradictions that logic struggles to resolve. The idea of branching timelines offers a way out, but it raises new dilemmas about identity, consciousness, and the nature of reality. If time is flexible, then what prevents history from collapsing into chaos? If time is fixed, then why do certain quantum experiments suggest otherwise? If the future can influence the past, then what does that say about the true nature of causality? No definitive answer has been found. What is certain is that time is far more complex than it appears. The straightforward sequence of past, present, and future may be an illusion, a simplified interpretation of a deeper, hidden structure that has yet to be fully understood. The paradoxes of time travel expose the fragile assumptions behind cause and effect, challenging the notion that reality unfolds in a single, unbroken chain. Whether time is a fixed dimension, a branching tree of possibilities, or something yet to be discovered remains an open question. But one fact is undeniable. If time travel is possible, then the understanding of reality itself will never be the same. If time itself is uncertain, if causality can be tangled in paradoxes that challenge the very logic of existence, then what happens when reality encounters the most extreme and unforgiving environment in the universe, a black hole? In the struggle between physics and the unknown, black holes represent the final boundary, a place where the laws of nature face their greatest contradiction. They swallow everything that comes near, stretching space and warping time. But what happens to the information contained in what falls inside? Does it vanish forever, erased from existence? If so, this would break one of the most fundamental rules of physics, the conservation of information. Everything that happens in the universe follows a strict law. Information cannot be destroyed. It can change form, be scrambled, or hidden, but it is never lost. A book can be burned, but the information it contained still exists in the chaotic dance of rising smoke and scattered ashes. A shattered glass can never be reassembled perfectly, but the information about its past shape still exists in the trajectories of its broken pieces. This principle holds at every level of physics, from the smallest interactions of quantum mechanics to the grand evolution of the cosmos. But black holes challenge this rule. When matter and energy fall into a black hole, they seem to vanish beyond its event horizon, the point of no return. No signal, no particle, no trace of what entered can ever escape. If nothing comes back out, does that mean the information is gone forever? If so, the very foundation of physics collapses, because it would mean the universe is capable of erasing history itself. The problem grows worse when considering that black holes are not truly eternal. According to Stephen Hawking's groundbreaking discovery, black holes slowly evaporate over time. They emit radiation, known as Hawking radiation, which causes them to lose mass and shrink. Given enough time, a black hole will eventually disappear entirely, leaving behind nothing. But if nothing remains, then what happened to the information that fell in? Did it simply cease to exist? If so, this violates the core principle of quantum mechanics, which states that information must always be preserved. This contradiction is known as the black hole information paradox, and it presents one of the most serious conflicts between quantum mechanics and general relativity. On one side, relativity dictates that nothing can escape a black hole once it has crossed the event horizon. On the other, quantum mechanics insists that information cannot be lost. These two fundamental pillars of physics clash, revealing a gap in the understanding of how the universe operates. Several attempts have been made to resolve the paradox. One idea is that information is not lost, but is instead encoded in the Hawking radiation itself. If this is true, then black holes do not truly erase what they consume. They simply transform it, releasing information in a highly scrambled form. However, for this to work, Hawking radiation must carry information about everything that fell in, a mechanism that is not currently understood within known physics. Another possibility is that information never really enters the black hole in the first place. Some researchers propose that the event horizon acts as a firewall, preventing information from being lost beyond it. In this view, anything that falls toward a black hole is either reflected back out in some form or remains imprinted on the event horizon itself. But this idea creates new paradoxes, as it suggests that the smooth, continuous nature of space-time breaks down near black holes, contradicting Einstein's theory of relativity. A more radical proposal is that black holes are not what they seem. Some physicists argue that what appears to be an event horizon may actually be an illusion, a dense structure where information remains encoded, rather than disappearing. If true, this would mean black holes are not true singularities, but instead complex quantum structures that store information in ways not yet understood. The holographic principle offers another potential resolution. It suggests that all the information contained within a volume of space can be encoded on its boundary, much like a three-dimensional object being represented on a two-dimensional surface. If this principle applies to black holes, then everything that falls in might still exist in some form on the horizon rather than being lost. This would mean that, in a way, the universe functions like a vast, multidimensional projection, where information is never truly destroyed, but merely rearranged in ways beyond current comprehension. Some researchers believe that quantum gravity, the yet-to-be-discovered theory that unifies quantum mechanics and general relativity, may hold the key to resolving the paradox. If space-time itself has a deeper quantum structure, then black holes may not erase information at all, but instead transform it in ways not yet understood. This could mean that the very nature of space and time changes at the edge of a black hole, preserving information in a form that has not yet been discovered. The paradox also raises profound questions about the nature of reality itself. If information is lost in black holes, then does that mean the past can be erased? Does it imply that the universe is not truly deterministic, that events can unfold without preserving a complete record? If information is preserved, then where does it go? If it is encoded on the event horizon, then does that mean black holes contain a hidden structure that remains to be uncovered? One of the most unsettling possibilities is that black holes might act as gateways to new regions of space or even entire new universes. Some theories suggest that information does not disappear but is transported elsewhere, beyond the observable universe. If true, then black holes may not be destructive endpoints, but rather transitions to unknown realms, where the laws of physics take on new and unexpected forms. Attempts to probe the paradox continue, with advances in observational astronomy offering new insights. The study of gravitational waves emitted when black holes merge may provide clues about their internal structure. Experiments with high-energy particle collisions aim to test whether information behaves differently under extreme conditions. The exploration of quantum entanglement and wormhole theories may one day provide answers to what happens to information inside black holes. The deeper the investigation goes, the more it becomes clear that black holes are not simply objects in space, but are instead the most extreme laboratories for understanding the nature of reality. They push physics to its limits, exposing contradictions that demand new theories. They suggest that space and time themselves may be more fluid, more interconnected, and more mysterious than previously thought. The paradox remains unresolved, but one thing is certain. Black holes are not the simple voids they once appeared to be. They are engines of transformation, places where information is reshaped, where physics encounters its most profound challenges, and where the very structure of existence is questioned. If black holes do not destroy information, then where does it go? If they do, then what does that mean for the laws of physics? If the universe forbids true information loss, then what unknown mechanisms preserve it? The search for answers continues, with the resolution of the paradox likely to reveal not just the secrets of black holes, but the fundamental nature of the universe itself. If black holes defy the laws of physics by seemingly erasing information, if the very fabric of space-time bends under extreme conditions, then what happens when physics itself proposes the existence of something that should not be possible, negative mass? The concept challenges everything understood about motion, gravity, and force. It suggests that an object, instead of resisting acceleration, would accelerate in the opposite direction when pushed. It implies that the fundamental laws of motion, established since Newton, might not be absolute. If negative mass is real, it could redefine the structure of the universe, reshaping the understanding of how matter interacts with space and time. In everyday experience, mass is always positive. Whether a small pebble or an enormous planet, objects resist changes in motion according to their mass. Newton's second law of motion states that force equals mass times acceleration. If a force is applied to an object, it moves in the direction of that force. But negative mass, if it exists, turns this principle upside down. Instead of moving in the direction of an applied force, it would move in the opposite direction. If pushed, it would not accelerate away, but instead toward the source of the push. This behavior is not just strange, it is entirely counterintuitive. A universe containing negative mass would allow for scenarios that break the conventional understanding of motion. If two objects of opposite mass interact, something bizarre happens. A negative mass object would push against a positive mass object in a way that continuously accelerates both. This runaway effect, sometimes referred to as negative mass propulsion, suggests that a system with negative mass could move indefinitely without any external energy input. One of the most unsettling consequences of negative mass is its interaction with gravity. In general relativity, mass warps space-time, creating the force of gravity. Positive mass attracts other positive mass, forming planets, stars, and galaxies. But negative mass, if it follows the same principles, would repel everything. A universe containing both positive and negative mass would behave in unpredictable ways. Large-scale structures might be held together not by gravitational attraction, but by an intricate balance of opposing forces. Another paradox arises when considering how negative mass would behave in response to gravity. In conventional physics, an object with mass experiences acceleration toward another mass due to gravitational attraction. But if mass is negative, then according to Newton's law of gravitation, it should experience a repulsive force instead of an attractive one. This means that a negative mass object should be repelled by all positive mass objects, drifting away instead of falling toward them. But an even stranger possibility emerges. If a negative mass object follows the same gravitational laws as positive mass, then in a gravitational field, it might accelerate toward a positive mass object while being repelled at the same time. This creates a feedback loop where the two objects move in a way that defies standard physics. The result is a system where negative mass behaves like an anti-gravity material, something that could theoretically counteract the effects of gravity entirely. The possibility of negative mass is not just a theoretical oddity. It has been explored in certain areas of physics, particularly in cosmology and quantum field theory. Some researchers propose that negative mass could explain the accelerating expansion of the universe. If negative mass exists in vast quantities, its repulsive effect could account for the force pushing galaxies apart, providing an alternative explanation to dark energy. In quantum physics, negative mass-like behavior has been observed under specific conditions. Certain materials, when cooled to near absolute zero, exhibit properties that mimic negative mass. Bose-Einstein condensates, a state of matter where atoms behave as a single quantum entity, have demonstrated effects where the mass appears to act in reverse. When energy is applied, instead of moving away from the force, the system moves toward it. While this does not confirm the existence of naturally occurring negative mass, it shows that, under the right conditions, matter can exhibit behavior that contradicts normal expectations. Negative mass also raises questions about momentum and energy conservation. If an object with negative mass gains speed in the opposite direction of an applied force, where does that energy go? If momentum must always be conserved, how does a system involving negative mass balance the equation? Some physicists propose that negative mass might exist in forms that allow energy conservation to hold, but there is no definitive framework that fully resolves these contradictions. The possibility of negative mass leads to speculation about exotic applications. If negative mass could be harnessed, it could provide propulsion without the need for fuel. A spacecraft equipped with a negative mass drive, in theory, could accelerate indefinitely by exploiting the self-repelling properties of such matter. This could mean faster than light travel, or at the very least, a revolutionary method of space travel where thrust is generated without expelling mass. In general relativity, solutions to Einstein's equations suggest that negative mass could play a role in stabilizing certain theoretical constructs, such as wormholes. A traversable wormhole requires a form of negative energy to keep it open. If negative mass exists and interacts with gravity in the expected way, it could provide the exotic matter needed to support these structures, allowing for shortcuts through space-time. Despite its contradictions, negative mass is not entirely ruled out by current physics. Some models propose that regions of the universe could contain negative mass particles without violating known laws. If such regions exist, they might be detectable through their gravitational effects. Observations of galaxy rotation curves and cosmic expansion provide hints that something beyond conventional matter is influencing the universe. While dark matter and dark energy are the leading explanations, negative mass remains a possibility that cannot yet be dismissed. Negative mass also challenges the nature of inertia. If force and acceleration behave in reverse, then how does motion work at a fundamental level? If a negative mass object resists force by moving toward it instead of away from it, then does it follow the same principles of kinetic energy as normal matter? If motion can be reversed in this way, does that mean there is a hidden symmetry in the laws of physics that has yet to be discovered? Attempts to integrate negative mass into existing theories lead to inconsistencies that highlight the limitations of current physics. Some approaches suggest that negative mass might not be stable, that it could exist only temporarily before decaying into positive energy states. Others propose that negative mass may only arise in highly specific conditions, such as inside black holes or in the early universe. The challenge is determining whether it is a fundamental property of reality or an emergent effect that appears under special circumstances. Some interpretations of quantum mechanics propose that negative energy states may be tied to the vacuum fluctuations of spacetime itself. If space is not truly empty, but filled with quantum activity, then regions of negative mass might emerge as temporary distortions. This could mean that negative mass exists at microscopic scales, appearing and disappearing in brief bursts, without forming stable structures. Another difficulty arises when considering how negative mass would interact with normal matter on large scales. If it repels positive mass, then galaxies containing both types of matter might develop regions where forces cancel out, preventing gravitational collapse, but also preventing the formation of stable structures. If negative mass exists in abundance, then why do observations of the cosmos not reveal its effects in clear ways? Despite these unresolved questions, the possibility of negative mass remains an active area of theoretical exploration. It represents one of the deepest challenges to the conventional understanding of physics, highlighting gaps in the ability to explain the full behavior of matter and energy. Whether it is an overlooked component of the universe or a mathematical illusion remains unknown. If negative mass is real, then it opens doors to possibilities beyond anything currently imaginable. It could reshape the understanding of force, gravity, and motion. It could provide new ways of traveling through space, new explanations for cosmic expansion, and new insights into the hidden structure of reality. If it does not exist, then its theoretical contradictions expose the limits of current models. showing where physics must evolve to achieve a deeper understanding of the universe. The search continues, with each discovery bringing new questions. Whether negative mass is a missing piece of physics or an impossibility that reveals the true nature of fundamental laws remains to be seen. But one thing is certain: if negative mass exists, it would rewrite the rules of reality in ways that challenge everything known about how the universe works. If negative mass shatters the rules of motion, if forces can act in reverse and objects can accelerate in ways that should be impossible, then what happens when matter itself refuses to take a definite form? In the world of quantum mechanics, certainty dissolves. A particle is not just in one place, it exists in multiple locations at the same time. It does not merely take one path, it follows every possible trajectory simultaneously. The reality that seems solid, predictable, and measurable unravels at the most fundamental level, revealing a world where common logic no longer applies. Quantum superposition is one of the most unsettling ideas in physics. It suggests that before measurement, a particle does not have a single definite state. Instead, it exists in all possible states at once. An electron is not confined to a single position. It is everywhere it could be, in a probability cloud of potential locations. A photon does not take a single route through space. It explores all available paths, interfering with itself as if it were multiple versions of itself moving in parallel. This principle is not just a mathematical curiosity, it is a fundamental aspect of reality that has been confirmed by countless experiments. The most famous demonstration of superposition is the double slit experiment. When particles are sent through two slits without being measured, they behave like waves, forming an interference pattern that suggests each particle is passing through both slits at once, but the moment an observer tries to determine which path the particle took, the interference pattern disappears. The act of measurement forces the particle into a single state, collapsing all other possibilities. This implies that reality does not settle into a definite form until it is observed. If superposition were limited to microscopic particles, it might be easier to accept as a quirk of the quantum world. But the principle has no strict size limit. In theory, even macroscopic objects could exist in multiple states at once, if they were sufficiently isolated from their environment. This idea is at the heart of Schrödinger's cat, a thought experiment that exposes the unsettling implications of superposition. If a particle can be both decayed and not decayed at the same time, then any system entangled with it, including a living organism, should also exist in multiple states simultaneously. A cat inside a sealed box, dependent on a quantum event, should be both alive and dead until someone looks inside. The thought experiment is not meant to suggest that cats actually exist in such a paradoxical state, but rather to highlight the absurdity of applying quantum rules to larger systems. One of the biggest mysteries in physics is why superposition appears to be limited to small scales. In theory, there is no clear boundary separating the quantum world from the macroscopic one. Yet, in everyday experience, objects do not exist in multiple places at once. The reason for this is believed to be decoherence, the process by which interactions with the surrounding environment cause a quantum system to lose its delicate state of superposition. The more particles involved, the harder it is to maintain quantum coherence. The moment an object interacts with air molecules, radiation, or any form of external influence, its wave-like behavior collapses into a single, definite state. But even though large-scale superposition is difficult to maintain, quantum systems continue to defy expectations. In laboratories, researchers have created situations where atoms, molecules, and even small biological structures exist in superposition for extended periods. These experiments suggest that the line between the quantum and classical world is not as clear as once thought. If it is possible to keep larger systems in superposition, then does this mean reality itself remains in a state of uncertainty until observed? The implications of superposition extend beyond philosophical debates. Quantum computing is built on the ability of quantum bits, qubits, to exist in multiple states simultaneously. Unlike classical bits, which are either 0 or 1, a qubit can be both at once. This allows quantum computers to process vast amounts of information in parallel, solving problems that would take classical computers an impossible amount of time. The power of quantum computation relies on the very strangeness of superposition, harnessing the ability of particles to explore multiple possibilities at the same time. Superposition also plays a crucial role in quantum cryptography, where information is encoded in quantum states that cannot be copied or measured without disturbance. The security of quantum communication relies on the fact that observing a quantum state inevitably changes it, making eavesdropping impossible without detection. The bizarre nature of superposition is being turned into a practical tool, shaping the future of technology in ways that classical physics could never predict. But if superposition is real, then what does this say about the fundamental nature of existence? If particles do not have definite properties until measured, then what is reality when no one is looking? One interpretation suggests that measurement does not merely reveal a pre-existing state, but actively creates it. This view implies that quantum reality is not an objective structure, but a process that depends on observation. If this is true, then what determines which possibility becomes real? Why does one outcome emerge while all others vanish? Some theories propose that all possible outcomes exist simultaneously in a vast, branching multiverse. Every time a quantum event occurs, the universe splits, creating multiple parallel realities where each possibility plays out. In one version of reality, a photon goes through the left slit. In another, it goes through the right. In yet another, it behaves as a wave, interfering with itself. If this interpretation is correct, then every quantum event is not just a random collapse, but a selection from an infinite web of possibilities. This idea leads to profound questions about consciousness. If the universe branches into multiple versions of itself, then why does human experience follow only one path? If all possible realities exist, then why does a conscious observer perceive only a single sequence of events? Some researchers speculate that consciousness itself plays a role in selecting which quantum outcome becomes real. This hypothesis, though highly speculative, suggests that the act of observation is not just a passive process, but an active force in shaping reality. There are also implications for the nature of time. If particles exist in multiple states before measurement, then does this mean the past is not fixed until it is observed? Some interpretations of quantum mechanics suggest that events in the present can influence the past, creating a form of retrocausality where future choices determine past outcomes. While this idea remains controversial, certain experiments hint that quantum systems may not be bound by the traditional flow of time. Superposition challenges the assumption that the universe operates according to fixed, predictable rules. It suggests that, at the most fundamental level, reality is fluid, undefined, and shaped by observation. The concept forces a re-evaluation of what it means for something to exist before it is measured. If particles do not have definite properties until they are observed, then does this mean that reality itself is incomplete without observation? If superposition applies to all things, then does this mean the entire universe is in a state of uncertainty, waiting for measurement to solidify into a single form? Despite decades of research, the true nature of superposition remains unresolved. Some physicists believe that the paradoxes it presents indicate that quantum mechanics is incomplete. that a deeper theory will one day explain why particles behave this way. Others argue that superposition is not a mystery to be solved, but a fundamental truth about reality that must be accepted, no matter how strange it seems. What is certain is that superposition is not just a theoretical abstraction. It is a real observable phenomenon with practical applications and deep implications for understanding the nature of existence. If quantum mechanics is correct, then every particle, every atom, and perhaps every structure in the universe exists in a web of possibilities, a sea of overlapping realities where anything that can happen does happen, until an observation locks one version into place. If reality is built on superposition, then what does this say about the world that is experienced every day? If everything exists in multiple states until measured, then what, ultimately, is real? The search for answers continues, but one thing is undeniable. Quantum superposition is not just a feature of physics, it is a doorway to understanding the very fabric of existence itself. If quantum superposition reveals that reality is not as solid as it appears, if the very act of measurement shapes what is observed, then what does this say about the universe itself? If fundamental particles exist in multiple states until observed, then is it possible that something vast, something unimaginable, exists just beyond perception, slipping through every attempt to measure or detect it? Modern physics suggests that what is seen, what is interacted with, what is known, makes up only a tiny fraction of reality. The rest remains hidden, an invisible force shaping the cosmos, a presence that accounts for nearly everything, yet refuses to reveal itself. The universe, it seems, is built not just on the known, but on the unknown. Dark matter and dark energy are the greatest enigmas in physics. The total mass of stars, planets, galaxies, and all observable matter combined accounts for just 5% of the total energy in the universe. The remaining 95% consists of something unseen, something that does not interact with light, does not emit or absorb radiation, and does not conform to the normal laws of visibility. It is not missing matter, nor an absence of energy, but an entirely separate component of reality, something that holds the structure of the universe together while simultaneously tearing it apart. Dark matter reveals itself through gravity. Observations of galaxies show that they spin too fast to be held together by the visible matter alone. If only regular matter existed, galaxies should have unraveled long ago, their stars flung outward by centrifugal forces. But they remain intact, bound by an unseen force exerting gravitational influence. The existence of dark matter is inferred from its effects. It bends light around it through gravitational lensing. It affects the movement of celestial objects. It accounts for the excess mass observed in galaxy clusters. Yet, despite its immense presence, it has never been directly detected. Attempts to understand dark matter have led to numerous theories. One possibility is that it consists of undiscovered particles that interact only through gravity and the weak nuclear force. Candidates include weakly interacting massive particles, WIMPs, which would be heavy and slow-moving, explaining their gravitational effects. Another possibility is axions, extremely light particles that could behave as a wave-like field filling the cosmos. A third idea suggests that dark matter could be composed of primordial black holes, objects formed in the early universe that exert gravitational influence without emitting light. Despite decades of searching, dark matter remains elusive. Direct detection experiments, which attempt to observe dark matter particles interacting with regular matter, have yielded no definitive results. Collider experiments, which probe high-energy particle interactions, have yet to produce any candidate particles that match dark matter's expected properties. Some researchers propose that dark matter might interact with itself through unknown forces, forming hidden structures and even entire invisible galaxies that coexist with the known universe. If dark matter is the hidden mass holding galaxies together, then dark energy is the force pushing them apart. The expansion of the universe was once thought to be slowing down, as gravity should act as a counterforce pulling everything inward. But in 1998, observations of distant supernovae revealed that the opposite was true. The universe is expanding at an accelerating rate. The cause of this acceleration remains unknown, but it suggests the presence of a repulsive force permeating space itself, a form of energy that defies all attempts to explain it. Dark energy is often associated with the cosmological constant, a term introduced by Einstein to counteract gravitational collapse in his equations of general relativity. When it was discovered that the universe was expanding, Einstein abandoned the concept, calling it his greatest mistake. But with the discovery of accelerated expansion, the cosmological constant was resurrected, this time not as a mathematical fix, but as an inherent property of space. One explanation for dark energy is vacuum energy, the energy of empty space itself. Quantum mechanics suggests that even in a perfect vacuum, particles constantly appear and disappear due to quantum fluctuations. If this energy has a repulsive effect on space-time, it could be responsible for the acceleration of the universe. However, theoretical calculations predict a value for vacuum energy that is vastly larger than what is observed, creating a major discrepancy that remains unresolved. Another approach considers the possibility that general relativity is incomplete. If gravity behaves differently on cosmic scales than it does in local environments, then dark energy might not be a separate force at all, but rather a sign that the laws of gravity require modification. Some theories propose that gravity itself weakens over vast distances, reducing its ability to counteract expansion. Others suggest that extra dimensions or hidden forces could be responsible for the accelerating universe. The interplay between dark matter and dark energy shapes the fate of the cosmos. If dark energy remains constant, the universe will continue expanding indefinitely, with galaxies drifting further apart until all matter becomes isolated in an endless void. If dark energy increases over time, a future scenario known as the Big Rip could unfold, where the repulsive force eventually overcomes all bonds, tearing apart galaxies, stars, and even atoms themselves. If dark energy decreases or reverses, cosmic expansion could slow, leading to a future where the universe contracts in a big crunch, collapsing back into a singularity. The search for answers continues through observational astronomy. The cosmic microwave background radiation, the afterglow of the Big Bang, provides a snapshot of the early universe, offering clues about the distribution of dark matter and the influence of dark energy. Large-scale galaxy surveys map the structure of the universe, revealing how invisible forces shape cosmic evolution. Future space telescopes aim to refine the understanding of cosmic acceleration, testing whether dark energy is truly constant or if it evolves over time. The mysteries of dark matter and dark energy challenge the most fundamental assumptions about reality. If 95% of the universe is hidden, then what is the true nature of existence? If galaxies are held together by an unseen force and space itself is expanding due to an unknown energy, then how much of what is perceived is only a fraction of the whole? If the universe is shaped by forces that remain undetected, then how much more remains to be discovered? Some researchers speculate that dark matter and dark energy could be linked, part of a single unified phenomenon that has yet to be understood. If space contains hidden properties, then dark energy may not be a separate force, but a feature of the fabric of reality itself. If dark matter is composed of unknown particles, then its connection to the quantum world may hold the key to solving the greatest mysteries of cosmology. Alternative theories suggest that the effects attributed to dark matter and dark energy might arise from unknown dimensions. If extra dimensions exist, then their influence on gravity could create the appearance of missing mass and accelerating expansion. Some proposals even consider the possibility that dark matter and dark energy are the remnants of a previous universe, a hidden imprint of cosmic cycles beyond the observable universe. Despite the challenges, the search for dark matter and dark energy is not just about understanding the cosmos, it is about understanding existence itself. If the nature of these unseen forces is uncovered, it could lead to a new era of physics, one where the universe is no longer a fragmented puzzle of known and unknown, but a complete and coherent reality. The cosmos is filled with questions that remain unanswered. If dark matter is detected, if its particles are identified, then the structure of galaxies and the evolution of the universe will be fully explained for the first time. If dark energy's origins are understood, then the future of the universe will no longer be a mystery. If both are connected, if they arise from a deeper layer of physics, then the next great revolution in science may lie just beyond the limits of current knowledge. The universe is vast, but the knowledge of it is still small. If dark matter and dark energy hold the key to understanding reality, then their discovery is not just a scientific goal, it is a step toward answering the most profound question of all. What is the universe truly made of? The search continues, and with every new observation, the unseen forces that shape existence grow closer to being revealed. If dark matter and dark energy expose how little is known about the structure of the universe, then an even deeper mystery emerges. Why does the universe exist in a way that allows for life at all? The laws of physics are not random. They are precise, governed by constants that seem to be set with an almost impossible level of accuracy. If any one of these fundamental numbers were even slightly different, stars would not form, atoms would not bond, and the complex chemistry needed for life would never arise. The cosmos, despite its vastness and mystery, appears to be balanced on a razor's edge. This is the fine-tuning problem. It is not simply a question of why the universe works the way it does, but why it works in a way that permits life to emerge. If the strength of gravity were slightly weaker, matter would not clump together to form galaxies. If it were stronger, stars would collapse too quickly, burning out before they could create the elements necessary for life. If the electromagnetic force were different by even the smallest fraction, atoms would not form stable molecules, and chemistry itself would not function. The ratios of these forces are not just convenient, they are essential, delicately balanced to an extent that defies intuition. The most unsettling aspect of fine-tuning is how many constants must align for the universe to function as it does. The speed of light, the charge of the electron, the mass of fundamental particles, and the cosmological constant all fall within an incredibly narrow range of values that allow stars to burn, planets to form, and biological life to exist. Any deviation, no matter how small, would lead to a universe that is sterile and lifeless. The question that arises is unavoidable. Why are these constants so precise? Is it mere coincidence, or does it suggest something deeper about the nature of reality? Some physicists argue that fine-tuning is simply an observational bias. The fact that the universe allows for life is not remarkable because, by definition, only in such a universe could life exist to ask the question. This is known as the anthropic principle, which states that observers can only exist in a universe where observation is possible. From this perspective, there is nothing special about fine-tuning. It is merely a condition for conscious beings to exist in the first place. However, While this explanation avoids the need for deeper reasoning, it does not provide an answer as to why the constants take the values they do. Another possibility is that there are countless other universes, each with different physical laws. If an infinite number of universes exist, then it is not surprising that at least one of them has conditions suitable for life. This is the multiverse hypothesis, a proposal that suggests reality is far larger than what is observable. If there are infinite variations of physical laws across different universes, then fine-tuning is no longer mysterious. It is simply a consequence of the vast number of possibilities. However, the challenge with this idea is that no evidence for these other universes has been found. If they exist, they may be fundamentally unobservable, making the multiverse a hypothesis that cannot be tested. Some physicists suggest that the values of fundamental constants are not actually arbitrary, but are determined by an underlying principle that has yet to be discovered. If a deeper theory of physics exists, it might explain why these values take the precise form they do. This would mean that fine-tuning is not a coincidence, but a necessity, dictated by fundamental laws that inevitably produce a universe with the conditions necessary for complexity. However, no such theory has yet been found, and whether it exists at all remains uncertain. Another perspective comes from the idea that the universe is designed, that the fine-tuning of physical laws is not random but intentional. This is a controversial proposition, as it moves beyond the realm of physics into philosophy and metaphysics. The idea that the cosmos was created with a purpose is an ancient one, but fine-tuning provides a modern framework for revisiting the question. If the constants of nature appear designed, then does that mean they were set deliberately? If so, by what mechanism and for what purpose? While science does not require design to explain the universe, the precision of these values continues to provoke debate. The implications of fine-tuning extend beyond physics. If the universe is structured in a way that is highly unlikely yet necessary for life, then what does this mean about existence itself? If the constants of nature are the result of chance, then life is an accident, emerging from a series of improbable conditions. But if these constants are necessary, if they could not have been otherwise, then life is not just a random occurrence, it is a fundamental feature of the cosmos. Some theories suggest that the values of fundamental constants may not be fixed at all, but instead evolve over time. If physical laws change, then the universe may have gone through different phases, where conditions were not always as they are now. This raises the question of whether fine-tuning is a temporary state, something that only exists for a brief period before shifting to a different set of conditions. If true, then life may only be possible in specific windows of cosmic history, emerging and vanishing as the properties of the universe fluctuate. Another approach considers the role of quantum mechanics in determining physical constants. If reality is shaped by probabilities, then the values of fundamental forces may be selected in a way that maximizes the stability of the universe. This would mean that the universe is not simply the result of fixed laws, but of an ongoing process where certain configurations naturally dominate. In this view, fine-tuning is not an unexplained coincidence, but a consequence of how reality self-organizes. The fine-tuning problem also leads to deeper questions about consciousness. If the universe is structured in a way that allows for the emergence of intelligent observers, then does this mean that consciousness itself plays a role in shaping reality? Some interpretations of quantum mechanics suggest that observation is not passive, but actively influences the outcome of events. If this applies on a cosmic scale, then does the presence of conscious beings somehow contribute to the universe taking its current form? This idea remains speculative, but it highlights how interconnected physics, philosophy, and the nature of existence truly are. Despite the mystery of fine-tuning, there is no consensus on its resolution. Some physicists accept it as an unexplained feature of the universe, while others search for deeper laws that might account for it. The debate continues, but the fact remains. Reality is balanced in a way that is extraordinarily rare. Whether this balance is the result of chance, necessity, or something beyond current understanding, the precision of physical constants remains one of the most profound and unresolved questions in science. If fine-tuning is real, then what does it say about the nature of the cosmos? If the universe is structured in a way that is perfectly calibrated for life, then does this mean life is inevitable? If the values of fundamental constants were different, then would another form of complexity have emerged? Or would the universe be an empty void? If the laws of physics were different, then would anything exist at all? The search for answers continues. But one thing is certain, the universe is not random. The fine-tuning problem challenges the idea that reality is a meaningless collection of particles and forces. It suggests that beneath the complexity, there is an order, a structure that allows existence itself to unfold. Whether this order is a product of deeper physics, an accident of probability, or something yet to be understood, the fact remains that the universe exists in a way that permits life, and that alone is a mystery unlike any other. The search for the nature of fine-tuning is not just about physics. It is about understanding why the universe is the way it is. If answers are found, they will not only change science, but the very way existence is perceived. The mystery of fine-tuning remains, waiting for the next breakthrough, the next discovery, the next insight that will reveal whether the universe is an accident, a necessity, or something beyond human comprehension. If the fine-tuning of the universe suggests that reality is balanced on a knife's edge, then an even greater question arises. What if this is just one of countless versions of reality? What if every decision, every quantum event, every possible outcome has not just one resolution, but infinite ones, all unfolding in parallel? The world that is seen, felt, and experienced may not be the only one. Physics suggests that, at the deepest level, reality does not collapse into a single version of events. Instead, it branches, splitting into an unimaginable number of alternate paths, each as real as the one that is known. Quantum mechanics is filled with mysteries, but one of the strangest is the way it deals with probability. A particle, before it is measured, does not exist in one definite state. It exists in superposition, in multiple states at once. When measured, it appears to choose one outcome, collapsing into a single version of reality. This is the way quantum physics has traditionally been understood. Measurement forces a particle into one state, while all other possibilities vanish. But what if they do not vanish? What if every possible outcome actually happens, just not in this version of reality? This is the core idea behind the many worlds interpretation. Instead of a single universe where probabilities collapse into one result, every possible outcome continues to exist in a separate, branching reality. If an electron has a 50% chance of being in one position and a 50% chance of being in another, then instead of choosing one, reality splits. One universe where the electron is in one position and another where it is in the other. This applies not just to electrons, but to everything. Every quantum interaction leads to a new branch, a new version of reality, where all possibilities play out. If this interpretation is correct, then the implications are beyond anything previously considered. It means that every moment of decision, every flip of a coin, every random quantum fluctuation creates a branching structure of realities. The universe is not a single, continuous thread, but an ever-expanding tree of diverging timelines, where all things that can happen do happen. The world that is experienced is just one among an infinite number, each evolving in its own direction. One of the strongest arguments for many worlds is that it does not require any additional assumptions beyond the existing framework of quantum mechanics. Traditional quantum theory requires a special rule, the collapse of the wave function, to explain why only one outcome is seen. But in many worlds, there is no collapse. Instead, the universe continues evolving according to the Schrödinger equation, with every possibility preserved in separate branches of reality. This makes it a simpler and more elegant explanation, avoiding the need for an artificial mechanism to explain measurement. Many worlds also provides a new perspective on probability. In everyday life, probability describes uncertainty about the future. But in this interpretation, probability is not about uncertainty, but about which version of reality will be experienced. If a quantum event has multiple possible outcomes, all of them occur, but an observer only experiences one branch. This suggests that personal experience is not about randomness, but about following one particular path through an infinitely branching reality. One of the most striking implications of many worlds is that it applies to human decisions as well. If every quantum interaction creates a split, then so does every thought, every choice, every action. In one universe, a person chooses one path. In another, they choose differently. Every version of every person exists somewhere in this vast multiverse, each living out a different fate. There are universes where history unfolded differently, where small changes cascaded into vastly different outcomes. There are realities where things went better, and others where they went worse. If all possibilities exist, then the concept of a single reality is an illusion. This raises profound questions about identity. If there are countless versions of the self, then what does it mean to be an individual? If every decision leads to multiple realities, then is there true free will, or is every choice merely a branching point in an endless cosmic structure? If consciousness exists in one branch, but also in many others, then what defines the experience of being a unique individual? Many worlds also has implications for time. If every quantum event creates new branches, then the flow of time is not a single line, but a constantly splitting structure. The past is not a fixed sequence of events, but a network of intertwined possibilities. If there are infinite versions of history, then is there a single true past? Or is the past itself a collection of parallel events? If the future is a branching structure of outcomes, then does this mean that all futures exist, waiting to be experienced in different versions of reality? One of the greatest challenges to many worlds is that it appears impossible to test. If alternate realities exist, they cannot be accessed from this one. There is no way to travel between branches, no way to observe other versions of history. Every observer follows their own path through the multiverse, with no awareness of the others. This has led some physicists to reject many worlds as an unscientific idea, arguing that a theory must make testable predictions to be meaningful. But others argue that many worlds does make predictions. It simply states that the laws of quantum mechanics apply universally, without exceptions. Some researchers propose that interference effects between parallel worlds might one day be detectable. If two branches of reality briefly interact, they could leave measurable signatures in quantum experiments. While no direct evidence for this has been found, the possibility remains open. If interference between parallel universes were observed, it would provide the first real test of many worlds. Another challenge is explaining why individuals only experience one version of reality. If all possibilities exist, then why does a conscious observer seem to follow a single path? One idea is that consciousness itself is a form of quantum process, tied to a particular branch. Each version of an individual exists in a separate reality, unaware of the others. Another possibility is that the process of observation itself, locks an individual into a specific version of events, preventing awareness of the branching structure. Many worlds also connects to the problem of quantum immortality. If all possible outcomes occur, then does this mean that some version of an individual always survives? If death is just another branching point, then there are realities where every person continues to exist indefinitely, no matter what happens. This idea is controversial, as it suggests that subjective experience never truly ends. Some physicists dismiss this as an illusion, while others see it as a natural consequence of many worlds. Despite its strange implications, many worlds remains one of the most mathematically consistent interpretations of quantum mechanics. It removes the need for arbitrary rules, treating reality as a seamless whole rather than a process that selects one outcome while discarding others. If it is correct, then the universe is far larger than imagined, not a single reality, but an infinite collection of them. The search for answers continues, but many worlds forces a rethinking of the nature of existence. If every possibility is real, then the universe is not a single entity, but an endless web of parallel histories, each as real as the next. If all choices are taken, then life is not a single path, but an infinite number of them. If quantum physics governs the structure of reality, then reality itself is far stranger than previously thought. Whether or not many worlds is correct, the question it raises is one of the deepest in science. What if reality is not what it seems? What if the world that is known is just one among countless others? If the universe is not a singular existence, but a limitless expanse of possibilities, then the search for meaning must extend beyond what is seen, beyond what is known, into the vast and infinite unknown. If the many worlds interpretation suggests that every possibility unfolds in parallel, then what happens when physics allows for something that should be impossible? If reality branches endlessly, creating an infinite number of possible timelines, then could there be a path where even the most fundamental cosmic speed limit, light itself, is not the ultimate barrier? What if motion beyond this limit is not just theoretical, but essential to a deeper understanding of the universe? The idea of particles moving faster than light is not just a science fiction fantasy. It is a real possibility buried within the mathematics of relativity itself. If such particles exist, they would defy the structure of cause and effect, altering the fundamental concept of time. Tachyons, hypothetical particles that always move faster than light, challenge the most fundamental assumptions of physics. In special relativity, the speed of light is an absolute boundary for anything with mass. An object moving at subluminal speeds cannot be accelerated past this limit, because doing so would require infinite energy. But the same equations that describe the impossibility of exceeding light speed also suggest that if something were already moving faster than light, it would never slow down below this barrier. In other words, tachyons, if they exist, are forever trapped in a superluminal realm, beyond the reach of anything in the observable universe. One of the strangest consequences of tachyons is their relationship with time. According to relativity, as an object approaches the speed of light, time slows down relative to an outside observer. For an object at light speed, time stops completely. But if an object exceeds this limit, time would, in theory, move in reverse from the perspective of some observers. This means that tachyons would not simply move through space faster than light. They would violate causality itself, potentially allowing effects to precede causes. If tachyons exist, then information could be transmitted instantaneously or even backward in time. A message sent using tachyons could arrive before it was even sent, creating paradoxes that challenge the very structure of reality. If a signal could be received before it was transmitted, it could alter the conditions that led to its own creation, disrupting the chain of events that define cause and effect. This suggests that faster-than-light motion is not just a question of speed, but of the fundamental ordering of events. Despite these paradoxes, the idea of tachyons has not been completely dismissed. The concept emerged in the 1960s when physicists exploring the implications of special relativity found that the equations did not prohibit particles that always move faster than light. These hypothetical particles would have imaginary mass, meaning that their energy calculations involve numbers that are mathematically valid but physically difficult to interpret. Instead of being a flaw in the theory, some physicists have speculated that tachyons might be real, but exist in a domain that does not directly interact with ordinary matter. Quantum field theory provides another perspective on tachyons. In some models, tachyonic fields do not necessarily indicate actual faster-than-light particles, but instead signal an instability in the vacuum state. In certain conditions, a system with a tachyonic field undergoes a transformation, reaching a more stable configuration. This idea plays a role in theories of cosmic inflation, where the early universe underwent rapid expansion due to a temporary vacuum instability. If tachyonic fields were present at the birth of the cosmos, they could have influenced the structure of spacetime itself, driving the inflationary period that shaped the large-scale universe. One of the biggest challenges in accepting tachyons as real entities is the lack of any direct evidence. If these particles exist, they should have some detectable effects on spacetime or interact with known fields in measurable ways. However, no confirmed experimental results have indicated the presence of tachyons, and attempts to incorporate them into a coherent framework of physics have encountered difficulties. Some interpretations suggest that tachyons might exist but remain permanently decoupled from normal matter, making them undetectable through conventional means. Another question surrounding tachyons is whether they could ever be harnessed for practical applications. If tachyons can carry information, then a tachyonic communication system could allow for faster-than-light messaging, rendering traditional notions of simultaneity meaningless. If an observer in one location sends a tachyonic signal to another observer far away, the message might arrive before it was sent, raising the possibility of communication across time. In some scenarios, tachyons could act as a medium for instantaneous knowledge transfer, providing access to information from different points in spacetime. Some speculative theories propose that tachyons could play a role in the deeper structure of reality. If they exist beyond the known boundaries of spacetime, they might be linked to hidden dimensions or alternate layers of physics. In string theory, certain modes of vibration suggest tachyonic properties, which are usually interpreted as indications that a system is unstable and will transition to a more fundamental state. This has led to proposals that tachyons may not be particles in the traditional sense, but manifestations of deeper processes in the quantum structure of the universe. The concept of tachyons also raises questions about the limits of relativity. While special relativity firmly states that no object with normal mass can exceed the speed of light, it does not explicitly forbid the existence of things that always travel faster. If tachyons are real, then relativity would not need to be discarded, but expanded to include a domain of physics that operates beyond the known constraints of spacetime. Some researchers have speculated that tachyon-like behavior might emerge in extreme conditions, such as near black holes or within the quantum foam of spacetime at the smallest scales. One of the most fascinating aspects of tachyons is their potential connection to the vacuum of space. If the universe contains a hidden structure of fields that govern its large-scale properties, then tachyons could be an indication of how these fields interact. Some models of dark energy suggest that the accelerating expansion of the cosmos could be linked to tachyonic effects at a fundamental level. If space-time itself has underlying instabilities, then tachyons might be a sign of transitions between different energy states in the fabric of the universe. The search for tachyons continues through both theoretical and experimental physics. While no direct evidence has been found, the possibility remains open that some form of faster-than-light phenomenon exists in ways not yet understood. The difficulty in testing for tachyons lies in their supposed nature. If they do not interact with ordinary matter, then how would they ever be detected? If they exist in a hidden sector of physics, then their presence might only be inferred through indirect effects such as subtle changes in the behavior of quantum fields or unexplained anomalies in particle interactions. The concept of tachyons forces a reconsideration of the nature of speed, time, and causality. If reality includes domains where superluminal motion is possible, then the strict separation between past and future may not be as rigid as previously thought. If tachyons do not violate fundamental principles but instead point to a deeper understanding of physics, then their existence could lead to breakthroughs in how space-time is structured. Even if tachyons remain theoretical, their presence in the mathematical framework of physics suggests that the laws of reality are more flexible than they appear. If tachyons are real, then they would redefine what is known about motion, information, and the limitations of speed. If they are merely a feature of equations rather than physical objects, then their existence still serves as a guide to uncovering the next stage of scientific understanding. The study of tachyons is more than a search for faster-than-light particles. It is an exploration of the edges of reality itself. Whether they exist or not, their implications reach deep into the structure of time and space, suggesting that the universe is not as straightforward as it seems. The search continues, but one thing is clear. If tachyons exist, they would challenge the very foundation of physics, offering a glimpse into a realm of motion and causality beyond anything previously known. For 3 hours, the fabric of reality has been stretched, twisted, and redefined. The boundaries of existence, once thought to be solid, have dissolved into paradoxes, hidden dimensions, and impossible truths. The measurement problem shattered the idea of a fixed reality. Wave-particle duality made it clear that matter itself refuses to conform to classical expectations. Quantum entanglement defied the limitations of space. Time dilation and length contraction dismantled the notion of absolute time. The arrow of time questioned why moments move forward and never back. Schrödinger's cat mocked the very concept of certainty. The double-slit experiment exposed the unsettling influence of observation. Vacuum energy proved that even empty space is never truly empty. The grandfather paradox forced a reckoning with time loops and causality. The information paradox dared to challenge whether black holes erase reality itself. Negative mass opened the door to objects that move in reverse. Quantum superposition declared that particles exist everywhere and nowhere at once. Dark matter and dark energy confirmed that most of the universe is utterly invisible. The fine-tuning problem asked why the cosmos seems almost too perfect. The many worlds interpretation suggested that every possible choice exists in parallel. Tachyons proposed a realm where faster-than-light travel isn't fantasy but necessity. The holographic principle whispered that everything known may be a projection from a deeper truth. Through all of this, one question remains: what is reality? If observation shapes existence, if time bends and breaks, if countless universes unfold alongside this one, then how much of what is seen, felt, and understood is merely a fragment of something greater? The nature of reality is not just a question for physicists, it is a question that touches everything: perception, experience, meaning itself. Now, it's your turn. Which of these concepts shattered your view of the universe the most? Drop a comment below, and let's keep this conversation going. Because if reality is this strange, then there is always more to discover. If you enjoyed unraveling the mysteries of existence, make sure to subscribe and hit the notification bell, because this is just the beginning. The universe is not done surprising you yet.